So we are going to study plastic analysis. In plastic analysis, what we'll study? First of all, we'll study shape factor. Shape factor. After that, we'll study collapse load. After that, we'll study length of plastic hinge. After that, we'll study. After that, we'll study that is mechanisms in frames. Okay. Now, first of all, we'll study shape factor. Now, what is shape factor? Shape factor is simply S. It's equal to Z of plastic divided by Z of plastic. Now, what is Z? Z means section modulus. Now, what does this section shape factor signify? It signifies capacity which is unused after elastic yielding. Okay, when the yielding occurs in any plastic body, then after that elastic yielding, how much is the remaining capacity of any section? That is the shape factor. That shape factor tells us. Okay, now how this will tell us? We'll see some shapes. Let's take uh, a rectangular. Let's take a rectangular shape. Okay, if you take a rectangular shape, you will see Z plastic. Z plastic. It's simply it's simply Z plastic is simply a by 2 y1 bar plus y2 bar. Now what does this mean? If we have any section, then we have the neutral axis of plastic section. Then we have neutral axis of plastic section. The area above it is A1 and the area below it is A2. Neutral axis of plastic section divides the section such a way that in such a way that A1 is equal to A2. Okay, this is the this is the property of plastic section. We have another section, that is elastic section. Elastic section, oh sorry, neutral axis of elastic section. Okay, this simply passes through CG. Okay, center of gravity. Now we'll see in a rectangular section what is shape factor. What is shape factor? Okay, we'll see in this rectangular section what is shape factor. Now let's make let's suppose this is the breadth of the section and this is the height of the section. Now if we see what is ZE, that is the section modulus on elastic yielding. Okay, so ZE will be called I about centroidal axis divided by y max. Y max is the distance between CG and outer fiber. Okay, now if you see this rectangular section, we'll take ICG about this axis. Okay, so ICG will be called B H cube divided by 12, and Y max will be called H by 2 because it's from center of gravity to this section. This is Y max, that is called H by 2. Therefore, ZE will be called BH cube divided by 12 whole divided by H by 2, which is called BH square divided by 6. Okay, this is the section modulus, elastic section modulus. Okay, this is RD. Now we'll find ZP. ZP is found using this relation. Why this relation? Okay, found this relation. Okay, so this is ZP. Okay, this is ZP. Okay. Now what will be the area? This is simply A by 2. That's B into H by 2. A is the area of whole section. This A is area of whole section. Area of whole section. Okay, B1 by 2. This will be called H by 4 plus H by 4. That will be called BH divided by 4. BH square divided by 4. Okay, so therefore ZP divided by ZE, which is shape factor for rectangular section, will be called ZP, that's BH square divided by 4 divided by ZE, which is divided by 6, which is equal to 6 by 4, 3 by 2, which is equal to 1.5. So shape factor for this rectangular section will be 1.5. Will be 1.5. So this is like this. We can calculate shape factor for any shape. We have shapes like this. We can calculate shape for this. We can calculate shape for triangle. We can calculate shape for circular. We can calculate shape factor for diamond. Now we'll go on another topic, that is collapse load. Okay. Now we'll go on collapse load. Okay. Collapse load. We'll take 3 to 4 examples in this case. Let's take example number 1. What's collapse load? Let's take example number 1. What's collapse load? Let us suppose this load W. This load W will be the collapse load when the movement at this will be MP. That means when the plastic hinge is formed at this location. Okay, when the plastic hinge is formed at this location. Okay, we'll use here principle of virtual work. Principle of virtual work that says external work done is equal to internal work done. Okay. Now, if you see in this case, the external work done is done by this load, this collapse load, which will cause a deflection of delta and a plastic hinge there. Okay, a plastic hinge will be formed under this load only because here we have a maximum bending moment. Okay, so W into delta, that is the deflection that the external load created, is equal to internal work done. Internal work done is created by this plastic hinge here. If you see, there are two moments and they have created, if this is the theta, if this is L by 2, okay, so they have created two thetas here. Okay, two thetas. Okay, so W will be W into delta. So if you see delta will be equal to theta L by 2 for smaller. Theta is very small, and take tan theta, which will be equal to theta. Okay, so W into theta L by 2 will be equal to MP into 2 theta. Theta will get cancelled. So we'll get W equal to MP 4 by L. If you see bending moment of this diagram, if you see bending moment of this diagram, that's maximum here, which is equal to PL by 4 or WL by 4. Okay, WL by 4. This is the case number 1. Similarly, let's take second case. Same, we have same beam, but we have a UDL. We have to find this WU such that plastic hinge is formed. Here plastic hinge will be formed at the center because here we have a maximum bending moment of WL square by 8. Okay. Now let's assume a hinge is formed here. Okay, a hinge is formed here. So let's take now by principle of virtual work. By principle of virtual work. Okay. By principle of virtual work. WU into half base into height is delta is equal to MP into 2 theta. Okay. So what is delta? Delta is again theta L by 2 is equal to MP into 2 theta. Theta will get cancelled. So WU into L square divided by 8 is equal to MP. So WU is equal to 8 MP by L square. This is the collapse load for this diagram. This is the collapse load for this diagram. Okay. This is the collapse load for this diagram. Collapse load. You can see MP is equal to WU L square by 8. As you can see, when our load is WU such that here the plastic hinge is formed, here the plastic hinge is formed. At the same time, the moment there will be the plastic hinge. You can check by this. This check you can check actually. Okay. Now let's go ahead and let's now have fixed load P here. Okay. Now let's suppose we have total length L. This is L by 2 and this is L by 2 here. Now let's see find collapse load. Okay. We have to find collapse load. We have to find collapse load. We have to find collapse load. First of all, we'll form a bending moment diagram because we don't know where the hinge will be formed, whether these three hinges will be formed simultaneously or not. Okay. So if you see the bending moment for this, first of all, this is BL by 8. Okay. Due to this point load and the hogging moment due to these two. I think this is the let's cut this moment diagram and we'll see the positions where the bending moment where the hinge can come in picture. This is the one position, second position, and third position. Here the hinge can come in picture. Okay. So we have, if you see by virtual work again, by virtual work, by virtual work, MP and how many thetas? If you see, one theta will be formed here, second theta, and third theta like this. Okay, this is L by 2. So actually we have how many thetas? One theta, two theta, three theta, four theta. We have four thetas. MP into four theta equal to P into theta L by 2. Actually, this is equal to delta, the deflection here. Okay. So if you see this P, which is the collapse load, is equal to 8 MP by L. This is the collapse load. Okay. This is the collapse load that is formed. That is formed at the collapse load. Okay. Now this is the end of this topic is over. This topic is over. Now we'll come to the length of plastic hinges. Length of plastic hinges. How we'll find the length of plastic hinge? Let's suppose we have a beam here. Okay, simply supported beam. Simply supported beam here. Okay, and we have a load P here. And let us suppose due to this, the bending moment diagram formed is. Let us suppose the plastic hinge is formed at this location, and these are the places where we have a working stress or working moment. Okay, so let us suppose for this region we have effect of this plastic hinge. Okay, we have effect of this plastic hinge. Let us suppose the distance from this is x. Okay, from both sides is x, and we have a total length of L by 2 L by 2. Let's suppose here is ME. Okay, this is the working stress or working moment. This is L by 2. Now you can see if you measure this distance, this is the length of this distance is the length of this distance is the length of hinge. So if we calculate the length of hinge, that will be equal to L by 2 plus L by 2 minus x minus x. Okay, L by 2 plus L by 2 minus this x minus this x, or we can say L by 2 minus x plus L by 2 minus x. This is the length of total plastic hinge, or we can say length of hinge is L minus twice x. Okay, L minus twice x. Okay, now if we see from this diagram, take use rule of similar triangles. If we see MP divided by L by 2 will be equal to ME divided by x. Okay, so if we see MP by ME is equal to L by 2x. Okay, if we see shape factor, we say earlier it's equal to Z elastic by Z plastic by Z elastic, or we can say it's also equal to MP by ME for same material strength. Okay, so which is equal to L by 2x. So we can find the value of x from here, which implies x is equal to L divided by 2 into shape factor. So put we'll put the value of x in this equation. So what we'll get is length of h is equal to L minus 2 into x. This is equal to L by 2 into s. 2 will get cancelled. Length of hinge will be equal to L into 1 minus L, 1 minus 1 divided by shape factor. Okay, so this is the length of shape factor. Let's find length of hinge for rectangular and I section. So length of hinge will be equal to L into 1 minus 1 divided by shape factor. Okay. For rectangular section, we know shape factor is 1.5. So if we calculate length of hinge, that will be equal to L divided by 3 after calculating these two. Similarly, if we see I section, shape factor will be equal to 1.16. Okay, so we can calculate length of hinge from this equation. Now we have a last topic here, that's mechanism in frames. Mechanism in frames. We have four types of mechanism in frames. First one is beam mechanism. Now what is this beam mechanism? Let's take any of the member, either it's column or beam. If the plastic hinge is formed in that, or the mechanism first happens in any one of the member, that's called as beam mechanism. Let us suppose the hinge is formed here only, here and here, which can cause the failure. Okay, three hinges are required here, so I need three hinges. So this failure isolatedly, or this failure, if we have load P applied here, this failure, either this failure or this failure, any of the two, but in a single manner. If it happens, then it's a beam mechanism. We have a second mechanism. That's sway mechanism. Sway mechanism means like this. So four hinges are formed. Four hinges are formed. We have another mechanism, that is combined mechanism. This is simply beam plus sway. Here three hinges are formed. One, two, and three. The hinge here is not formed because the moment decreases. Due to this combination, the moment decreases. Okay, that is one moment comes in clockwise due to this load, and one moment comes in anti-clockwise due to this load. So the effective load becomes very less. That's why the plastic hinge is not formed at this corner. Okay, so only three hinges are formed, and this can also cause. And here one plastic hinge, and this can cause. This will remain 90 as it is. This will cause the failure like this. Okay, and we have last mechanism, that's cable mechanism. When the both legs will go like this, both columns, okay, and this will go like this. This is called as cable mechanism. Okay, now we have a one question on this. Okay, we'll do this and this will conclude our plastic analysis completely. Let us suppose these are our loads. Okay, let's suppose these are our loads, W1 and W2. Now we have to find the collapse load. Find collapse load. We have to find collapse load. Find collapse load. Find collapse load. Okay, we have to find collapse load. How will we find collapse load? We know here three cases are possible. Let us suppose beam mechanism happens only. Second is sway happens only. Third is combined. We'll go first with beam mechanism. We'll go first with beam mechanism. Let's go 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 with beam mechanism. Okay. If we go with beam mechanism, if we go with beam mechanism, if we go with beam mechanism, okay. If we go with beam mechanism, you can see the failure will occur here, here, and here in beam mechanism. Okay, in beam mechanism, I'm specifically in beam mechanism, the failure will occur in these three positions. So, what will be our equation or collapse load? You will see W times the deflection will be equal to plastic moment times 4 theta. 4 times theta. Okay, 4 times theta will be the deflection. Okay, 4 times theta. So if we take the lengths as this is L by 2, this is L by 2. Let's take this also L by 2. Okay? So our W times theta L by 2 will be equal to MP into 4 theta. Theta will get cancelled. So W will be 8 MP by L. 8 MP by L will be the beam mechanism. This will be the failure due to beam mechanism only. Independent mechanism. If you go through sway means Sway means this will fail, this will fail, this will fail, and this will fail. These four will fail, and these will cause sway. These will cause sway mechanism. Okay, these will cause sway mechanism. Okay, if these will cause sway mechanism, then our MP times MP times how many thetas? Two thetas. MP times two thetas. Not two thetas. It will be three thetas. Okay, sorry, four thetas. Four thetas will be called W into theta L by 2. Now how this will be 4 theta, I'll tell you. If you see here, this will be the deflected shape after the sway. The hinge is formed here. The hinge is formed here. One moment will be here. Another moment will be here. Okay. Similarly, one moment will be here and another moment will be here. So these four moments, and there are obviously rotations as well. So these four have gone through the deflections, or we can say translations, not translations or rotations, due to these MPs. So this will be 4 times theta, and this will be, so we will get W is equal to 8 MP divided by L. Okay, we'll get 8 MP by L. We'll get 8 MP by L. We get 8 MP by L. Now let's have a combined mechanism. Let's have combined mechanism now. If we see the combined mechanism, only three hinges will be formed here. One hinge, two hinge, sorry, four hinges will be formed. Three hinge and four hinge. Four hinges will be formed. So our MP times what? Here will be the 1 theta. Here will be 2 thetas. Here will be 2 thetas. Here will be 1 theta from this side and 1 theta from this side. 2 thetas as well. Theta, here will be 2 theta at this end and 1 theta at this end. So these will be 6 thetas. Is equal to W into theta L by 2 plus W into theta L by 2. This will get cancelled. This will get cancelled. So our W will be equal to 6 MP by L. So the combined mechanism will occur first. Okay, the combined mechanism will occur first. So what will be the C? What will be the pattern of occurrence of these collapse mode? First of all, we'll get combined mechanism. Then we have the same two. So we'll get combined mechanism. This will consist of both beam as well as the sway mechanism. So the combined mechanism will occur. Okay. So this will be the failure. Failure will be of this type. Okay. Thank you.